we're going to start looking at work, energy, and power. So it's part of mechanics. And here we go. So, Unit 1, when we look at work, we often think that when we go home and we do homework, that we're doing work, and perhaps we are, but that's the English sense of the word. Work for us in terms of physics is different. When work is done, in order for work to be done in physics, what we need is we need a force to act on the object, and we need the object to move in the direction of that force. So there has to be movement and there has to be a force. When we look at an example of an object on a table, now remember, my object could also have a downward force because, of course, there's gravity, but that really is irrelevant because the point here is that the object isn't moving. It's not going up or down, which therefore means that no work is being done even though a force has been applied. If we now look at the same object that's being picked up, there is a displacement, there's movement upwards, and there's an upward force. That means there's now work being done in the science sense of the word, where we say where now there's force and displacement in the same direction. However, if I'm still applying an upward force and my object moves sideways as shown here, so my girl is holding the object upwards but is moving to the left with the object, still no work is being done because the displacement is at 90 degrees to the force. Remember, what we said in the first part is that the force and the displacement must be in the same direction. So that gets us to a definition. Now this is starting to get us to the official definition, which says to us, if a constant force acts on a body and it undergoes a displacement, then the work done by this force can be defined as followed. So here we have the situation with a box. Okay, here's my force. Now remember, when we look at this, we're actually concerned with the horizontal force. And we've done earlier that my horizontal force is F cos theta. Remember, when we put it into its components, the horizontal force is F cos theta. So theta is really important because we're looking at the horizontal displacement. So that tells us the work done on an object by a constant force is F delta x cos theta, where F is the magnitude of the force, delta x is the magnitude of the displacement, and theta is the angle between the displacement and the force, which is really, really important. That gets us to our equation, where W equals F delta x cos theta. W is work, which is measured in joules. F is force, measured in newtons. And delta x is displacement, measured in meters. Those are all important. And theta is the angle between F and delta x. Please note, work is a scalar, therefore it has no direction. However, work can absolutely be negative. It's the only scalar we work with that can be negative because the negative tells me about how the energy is either being put into the system or being taken out of the system. So it's very, very important. Work done is energy transferred. Now this energy could be transferred to the system, which means maybe it speeds up, or it's energy that's taken out of the system, which means that either it slows down or we have a transfer of heat, we get sound, all of those sort of things. Okay, so you need to work through the activity. The memos are on Teams. Okay, if we look at network, there's a couple of ways we can do that. So there's always a lot of forces acting on an object. Those forces, we've learned before, can be net forces. Okay, so we've got to look at the effect of direction of a force and the displacement. When the force is in the same direction as the displacement, so my force is going to the right and my displacement is to the right, F and X are in the same direction, which I've said before, delta theta is 0 and cos theta equals 1. All right, because cos 0 is 1. Positive work is being done. That means we are adding energy to the system. Okay, we're giving it extra energy. When they're in opposite directions, so the force is to the right and delta X is to the left, so this would be something like friction, which always acts in the opposite direction. That means theta is now 180, and cos 180 is minus 1. That means that negative work is being done. That means that we are taking energy out of the system. So kinetic energy, for example, is becoming heat. The total energy of the system is decreasing, all right? And it's going to the surroundings. Then we get perpendicular displacement and forces. Now here, and this is just an MB, remember friction is always at 180. Friction acts, say, to the right, and the displacement is down. Please, or the force acts to the right, displacement is down. There's lots of ways we can do this. We're not going to worry too much about where this happens. You'll see them as we go along. But here, friction, the force could be left or right, and the displacement could be up or down. It doesn't matter. The point here is that F and delta X are perpendicular, which means theta is 90, and cos 90 is 0. So no work is done by this force. All right? Because this force, this displacement at 90 degrees to each other. So let's look at an example. Here we have a boy pushing, or a person pushing a very large block of ice. Let's just go with it, all right? They tell you they want the work done on the block of ice, not by the block of ice, by the person exerting a force. So once again, it's really important to see what's important. So we're exerting a force of 25, displacement is 5, and we have an angle of 25, okay? Oh,